Welcome to Physics 191, General Physics 1. My name is Professor Gerard Blanchard, Professor of Physics at Southeastern Louisiana University. And if you are enrolled in Physics 191 for credit, then please refer to your course syllabus for course information. The topic of General Physics 1 is essentially motion and related topics such as force, momentum, and energy. And these are referred to collectively as mechanics, so that is the topic of General Physics 1, mechanics. In this course, I assume no prior knowledge of physics from the students. However, I do assume skill in algebra, arithmetic, and trigonometry. You may be watching this course for a variety of reasons. You may be enrolled in Physics 191. You may be preparing yourself to take physics in the future. You may just want to learn about the world around you. You may want to increase your skills in mathematics, and all those are very good reasons for learning physics. Regardless of the reason why you're watching this course, it's important that you watch actively. Physics is a mental exercise. You have to visualize, you have to use analytical logic, you have to use math skills, and all of these activities improve through exercise, through practice. So when I say watch actively, I encourage you to have a pencil, a paper, calculator, and try to work the exercises as we go through them. Try to stay ahead of me. If you make a mistake, that's fine. In fact, it's good, because when you make a mistake and learn from it, then you've learned. You know that you've learned something. If you don't make any mistakes, you haven't learned anything. So try and stay ahead of me. Do your best, be active. Decades of physics education research have shown that the key to learning physics can be summed up in two words, and those are active learning. Now, as you develop physics skills, you should start to see physics in your everyday world. Everyday activities such as driving a car, opening a door, throwing a ball, walking upstairs, all of these are good examples of physics at work. So I will encourage you often to think physics, and you will develop physics skill that way as well when you start to see physics in your everyday world. Now first, we'll have a short discussion of the fundamentals that we'll use throughout this course. The first fundamental that we have to talk about are measurement units. In physics, we're often dealing with quantities. And what a quantity is, it is a number and a measurement unit. In physics, in the metric system, the SI, System International, as I'll refer to it, all of those are ways to refer to the metric system. There are three basic units of measurement, and these basic units of measurement are the meter, a unit of length, the second, a unit of time, and the kilogram, a unit of mass, or the amount of substance that there is in an object. And these three basic units basically tell you what we'll be doing in this class. We'll be dealing with the motion of objects through space and time. And that is what mechanics is all about, motion of objects through space and time. Now, these three basic units, the meter, the kilogram, and the second, will form all of the units that we will deal with in the rest of this course. Now, some things such as velocity or speed will be measured in what we call compound units. For example, speed or velocity is measured in units of meters per second, or a length divided by time. Now, you may think of speed in terms of miles per hour, kilometers per hour. All of those are units of length divided by time. The basic metric unit of speed is the meter per second. And as I will encourage you in the next slide, you should always convert, or I recommend that you always convert your quantities to basic metric units, and I'll explain why in a moment. So units such as meters divided by seconds or meters per second, those are referred to as compound units. Other units, such as the unit for force, which is a Newton, is called a derived unit. It's actually a compound unit that we've given a new name to. The Newton is actually a kilogram times a meter divided by a second squared. That's a lot to write down, so for convenience sake, we simply have given that a new name, the Newton, and we symbolize that with a capital N. Or if you write it out, you can write out Newton, but use a lowercase n. Physical units that are given names, Isaac Newton in this case, the unit is always written with a lowercase letter to distinguish from the person. I always encourage you to convert the quantities that you're given in exercises to basic metric units. And the reason for that is that your calculator often doesn't work with units, it only works with the numbers. And the same quantity will have different numbers depending on the units that you use. So if you use the wrong number, then you will not work the exercise correctly. So for example, here we have two quantities that are not in basic metric units. For example, we have 1.54 kilometers, and we want to convert that to the basic metric units of meters. The way that we do that is to multiply the quantity 1.54 kilometers by the number 1, but we use a very special form of the number 1. And what we do is to write down what we know, and that is 1 kilometer is equal to 1,000 meters. That's what you would find in a table of conversions. 1 kilometer equals 1,000 meters. Now, the way that we get the number 1 that we're going to use for our conversion factor is we divide both sides of that by 1 kilometer, and we still have an equation. What is on the left side is still equal to what is on the right side. We started off with a proper equation, 1 kilometer equals 1,000 meters. That's valid. We divided both sides by the same thing, which means that we still have a valid equation. And now we have 1 kilometer divided by 1 kilometer. Anything divided by itself gives you the number 1. So 1 is equal to 1,000 meters divided by 1 kilometer. So 1,000 meters divided by 1 kilometer is the same thing as the number 1. It is numerically equal to 1. So now we can take our quantity, 1.54 kilometers, and that's equal to 1.54 kilometers. So far, so good. That's equal. And we're going to multiply it by the number 1, which will maintain our equality. But we're going to multiply it by the form 1,000 meters divided by 1 kilometer. So 1.54 kilometers is equal to, and what we'll do is we'll collect our numbers. Everything here is multiplied and divided, so we'll use our commutative property to write this as 1.54 times 1,000. We've gathered our numbers together, and then we have our units. We have meters, and then we have kilometers divided by kilometers. And I actually have another number 1 there, but I don't have to write that because anything divided by 1 is also equal to itself. So now what I have here is I have kilometers divided by kilometers. Once again, anything divided by itself is equal to the number 1. So I have 1.54 kilometers is equal to 1.54 times 1,000, 1,540 meters. So we have now converted 1.54 kilometers into the basic metric units, which would give us 1,540 meters. Now that seems like a long process. You might say, oh, I could have done that in my head. What that is doing, though, is taking a shortcut. Now, what you should remember is that taking shortcuts is okay as long as you know exactly where you're going and what you're doing. It takes practice to be able to take a shortcut. The danger with taking a shortcut is that you might get lost and then you don't know where to go to get where you're going. So as long as you follow the procedure, you will stay on the main streets, and then if you make a wrong turn, you can backtrack and find your way to your destination. If you take a shortcut, you might be really lost. Now, let's take a look at the next quantity, 30 centimeters. Now, I would like you to convert that to basic metric units. Please try. Now, in order to convert 30 centimeters into your basic metric units of meters, you'll need to use a conversion factor, which you might remember is 1 centimeter is equal to 1 over 100 meters. That's the meaning of centi, 1 over 100. And in order to get our number 1 out of this, we have to divide both sides by centimeters. And once again, as you can see, we have centimeters divided by centimeters. That gives us 1. Anything divided by itself is 1. And 1 times 1 is 1. So we have 1 on this side. And 1 is equal to 1 meter divided by 100 centimeters. And that is the number 1 that you'll need to convert 30 centimeters into meters, or 30 centimeters is equal to 30 centimeters. So far, so good. Everything on the left side is equal to everything on the right side. Now we multiply by the number 1 using our special form of 1 meter divided by 100 centimeters. And we have 30 centimeters is equal to, we gather up our numbers, 30 times 1 is 30, divided by 100, and we have meters. And then we have centimeters divided by centimeters. Anything divided by itself is 1, so I could write a number 1 and multiply it by a number 1, but I don't have to. So we'll just leave it at that. And we have 30 centimeters. 30 divided by 100 is 0.30 meters. So we've converted our 30 centimeters into our basic metric unit of 0.3 meters. Once again, I always encourage you to convert the quantities that you're given in an exercise to basic metric units so that you know that everything is in the same units. I will often, when working out an exercise, will at some point not write the units so that we don't have the clutter of the units in our equation. But I only do that after I've converted all my quantities to basic metric units. Now, we will have to deal with units in equations. And as you have here on this slide, you have 3 equations that have numbers and units in them. Try working out the first equation. 2 meters plus 6 meters per second times 3 seconds. I'll give you a little bit of time to work that out. Please try and stay ahead of me. If you can stay ahead of me, you're doing very well. Okay, what we do here is we write 2 meters plus 6 meters per second times 3 seconds, and that is equal to 2 meters. And we can collect our numbers here. We have 3 times 6, or plus 3 times 6, and we can collect our units. Meters times seconds per second, and seconds per second, as always, is the number 1. So we can write that as 1. And then we have 2 meters plus 18 meters. And what we can do here is we can factor out our meters. So that would be 2 plus 18 times meters. Since both of these quantities are multiplied by meters, I can factor that out, and I'm left with 2 plus 18 meters, and that would be 20 meters. Now try the second equation. 2 meters plus 6 centimeters per second times 3 seconds. Try to work that one. Try to stay ahead of me. Okay, 2 meters plus 6 centimeters per second times 3 seconds is equal to 2 meters plus, we have 6 times 3. We gather our units again, centimeters times seconds divided by seconds. Seconds divided by seconds gives us the number 1. We're just multiplying by 1. I don't have to write that anymore. And then we have 2 meters plus 18 centimeters. Now, what we have here is we have 2 different units. We can't factor out the units now because they're not the same. The 2 is multiplied by meters, while the 18 is multiplied by centimeters. So what we have to do is we have to convert our centimeters to meters before factoring out the meters and adding. So I will multiply by 1 meter divided by 100 centimeters, just as we did on the last slide. And now you can see what we have. We have 2 meters plus 18 divided by 100 meters times centimeters divided by centimeters. And once again, centimeters divided by centimeters gives us 1. And now we do have the same units and we can factor it out. We have 2 plus 18 over 100 meters, or 2.18 meters. So be very careful. 2 meters times 2 meters plus 6 meters per second times 3 seconds is different than 2 meters plus 6 centimeters per second times 3 seconds. Even though you had the same numbers, you had different units. So you would always want to be careful to convert to basic metric units. It's actually better to do that before you even start working in the equation. But if you wind up with an equation where you have to convert in the equation, that's okay. Now, try to work the last equation, which would be 2 meters plus 6 meters per second times 3 seconds squared. I'm only going to give you a little bit of time to work this one, and you'll see why in a second. Okay, here we have 2 meters plus 6 meters per second times 3 seconds squared. That's equal to 2 meters plus 6 meters per second. Now, order of operations tells us that we have to do the squared first, and notice that both the 3 and the seconds are squared. So we would have to write that as 3 squared seconds squared. And that gives us 2 meters plus 6 meters per second times 9 seconds squared. Gather up our numbers. 2 meters plus 6 times 9, and we have meters times seconds squared over seconds. Now, I'll write the second squared as seconds times seconds. 2 meters plus 6 times 9 meters times seconds divided by seconds. And the seconds in the denominator only cancels out one of the seconds in the numerator, so that we're left with 2 meters plus 6 times 9 meters times seconds. If we were to factor out the meters, then we would have 2 plus 6 times 9. We're factoring out the meters, but we can't factor out the seconds, so we have to leave in the seconds. And you can see that we're left with the number 2 plus 6 times 9 seconds. We have incompatible units, and there's nothing we can do there. We can't convert seconds into meters. We can't convert seconds into any number. What we have is a problem with our equation. That means that our original equation is invalid because of the units. So if you look back at the original equation, 2 meters plus 6 meters per second times 3 seconds quantity squared, that's not a valid equation. That is a non-physical equation. So what you should recognize is if you wind up with an equation where your units are incompatible, there's a problem with your equation. You have an invalid equation, and you should go back and find out at what point a mistake was made. There has been a mistake made. Something is not correct, and that's why it's important to work carefully so that you can always go back and find your mistakes. But the important lesson here is if you wind up with an equation with incompatible units, then there has been a mistake. That's not a physical equation. Now, in this course, I will teach you a small number of general principles of physics, each with its own equation, And then I will also teach you the procedure for applying these equations to an infinite number of particular situations. There's very little to memorize in physics. And in fact, if you were taking this course for credit from me, I will have open book tests. I don't expect you to memorize anything. I expect you to work through the book. I expect you to know where important things are in the book so that you can reference them, you can refer to them, but you don't have to memorize them. There's very little to memorize in physics. There will be a very small number of equations that you use, but you can apply them to an infinite number of situations. And the way that we do that is whenever you're given an exercise, the first step in solving it is to make what we'll call a mathematical model of the situation. And then you will work linearly using algebra, trigonometry, and arithmetic, and correctly. So you have to do all of that to solve your exercises correctly. You have to make a correct model, a proper model of the particular situation that you're given. You have to identify which of the general principles is applicable in that exercise, and then you have to work your math correctly. When I talk about making a mathematical model, what I mean is that when you have a particular situation that's described in the exercise statement, the first thing that I encourage you to do is to draw a diagram. Draw a diagram with all the forces involved in it. List all of the knowns and unknowns that come out of the exercise statement. Identify the type of problem that you're dealing with. What general principle is applicable to this situation? You write the starting equations that are applicable to that situation, and then you make the equations specific to the situation. What that means is you use your knowns and unknowns to fill in the equation. And you'll get a lot of practice on that. That's what we'll be doing throughout this course, is we will be taking exercises, we'll be taking situations, and we'll be applying physical principles to them by building a mathematical model. Now finally, before we get started with our physics, there's one more concept that's going to come up quite often in this course, and that is insignificance. In many cases, you'll be told to ignore friction, ignore air resistance, ignore the mass of a pulley, ignore the mass of a rope, or you'll be told that friction is negligible, the mass of the pulley or the rope is negligible. All of these mean the same thing, that the air resistance, it doesn't mean that it doesn't exist, it means that it's insignificant, and that means that it doesn't change your answer within your significant figures. So an example of this is, suppose that you have a truck scale that weighs to the nearest half of a ton, to the nearest 1,000 pounds. Now you're weighing a truck to the nearest 1,000 pounds, and a bird lands on top of the truck. Did that change the weight of the truck? Yes. Did it change the weight of the truck significantly? No. The reading that you get on the scale is going to be the same. The bird is not going to change the reading of a scale that reads to the nearest 1,000 pounds. So the weight of the bird is insignificant. And that's a term you're going to hear a lot. Often, as I said, we'll talk about friction or air resistance being insignificant. It doesn't mean that they don't exist. It means that they're not significant. They won't change your answer. It takes some practice to recognize when something is insignificant. Most often, the exercise statement will tell you that. You'll be told the keywords are to ignore something, that something is negligible, or that something is insignificant. Okay, our first topic of physics is force. You may remember from high school, you may have heard the definition. Force is a push or pull. That's good enough. We can start with that. Force is any push or pull. And as I've said before, force is measured in units of newtons. 1 newton is equal to 1 kilogram times meter divided by second squared. Now, here's the question. What is 10 newtons of force plus 10 newtons of force? Think about that for a second. 10 newtons of force plus 10 newtons of force. The answer is that 10 newtons of force plus 10 newtons of force could be anything from 0 newtons of force up to 20 newtons of force. Now, you might ask, how can that be? Well, let me demonstrate what I mean by that. We'll take this weight here, and I'll apply a force of 10 newtons to the left. So I'm pushing to the left with my finger with 10 newtons, more or less, of force to the left. Now I'm going to add in 10 newtons of force to the right. So now I'm pushing on this weight with 10 newtons of force to the right plus 10 newtons of force to the left, and the total force on the weight is 0 newtons because 10 newtons to the left plus 10 newtons to the right cancel out to give us 0 newtons of force total. However, if I were to push with 10 newtons of force to the left and then add in another 10 newtons of force to the left, now, since both of those are pushing to the left, they add together, and that would give us a total of 20 newtons of force to the left. I could even push with 10 newtons of force to the left and 10 newtons of force away from me. Now, those will add up actually to 14.1 newtons of force, and we'll get to why that is in a moment. But the important thing here is that force is what we would call a vector, and that means that the direction of the force is important, whether it's a force to the left or a force to the right. The 10 newtons of force doesn't tell you everything you need to know about the force. You need to know the direction of the force. And so any quantity that has both an amount, such as 10 newtons, and a direction, such as to the right or to the left, is what we call a vector. So a vector has both direction and magnitude. Magnitude is the word that we use in physics to mean amount, the bigness, the amount of force that there is. So a vector has direction and magnitude, or, as we'll see, a vector has two components. So a vector is always represented by two numbers. Now we will model our vectors mathematically as a right triangle. Now what I mean by that is here I've drawn our vector force as an arrow going from the origin of our x and y axes off at some direction. The length of the arrow we draw proportionate to the magnitude or the amount of the force. If there were a greater amount of force, we would draw a longer arrow. If there were less force, we would draw a shorter arrow. And then from that we can make a right triangle with legs that are parallel to the x-axis and to the y-axis. And that gives us a side that is adjacent to the angle and a side that's opposite the angle. The side that's adjacent to the angle I've drawn here as FA. That would be the component of the force adjacent to the angle. And the side opposite the angle would be FO, or the component of the force opposite the angle. And then we can use our trigonometric functions. I'll draw that again here on paper. We have the side of our triangle that is equal to the magnitude of our force. And then we have a side parallel to x. There's our angle theta. We have the adjacent side and the opposite side. And now we can use our trigonometric functions. So for example, the sine of theta f would be equal to the opposite side over the adjacent side. And we can solve that for the opposite side by multiplying both sides by force. So the magnitude of the force times the sine of the angle theta F is equal to our opposite component. We can use our cosine function. Cosine of theta F is equal to the adjacent side divided by the hypotenuse, which we can solve for the adjacent side as the magnitude times the cosine of theta F is equal to the adjacent side. Now, why would we want to do that? Why are we bothering with the adjacent side and the opposite side? The reason is that we can break down any force or any vector into two forces, one that is along the x-axis and one that is along the y-axis. So, a force that is directed at an angle of theta F relative to the x-axis is the same as a force in the x direction plus a force in the y direction. Now, this may not seem intuitive when we're talking about forces, but let's talk about another vector, which is displacement, or how far something is moved. If we talk about moving a certain distance at a certain angle, move a certain distance at a certain angle from here to here, that is the same as moving first in the x direction and then moving in the y direction. So moving from here to here is the same as moving a certain distance in x and then moving in y. And just as it's true for motion, which is also a vector, it's also true for forces. So we will work more with forces next time, and until then, think physics.